a higher order differential equation or a system of higher order differential equations can always be converted to a system of first order differential equations, but with some extra unknowns. So whenever you introduce one more unknown, you can reduce the order of the system by one. Right? So for example, and it's very simple, right? So if you have a third derivative, like here, right? So if you have a third derivative, x triple prime. So in order to get rid of x triple prime, x double prime, and x double prime, you will have to introduce more unknowns. So what you are going to have to do, you're going to have to write that x prime is u, x double prime, which is u prime, is going to be some v, and now x triple prime is going to be v prime. Right? So originally we only had one equation of order 3, and then whenever we introduce one more unknown, we can reduce the order by 1. So if we want something of order 1, then we have to do it twice. So we'll have to introduce two more equations. Sorry about that. It is important because for systems of first order equations, we have our Picard-Lindelöf theorem. So remember that in week 5, I think that there was a TBL session when we went through the proof of the Picard-Lindelöf theorem, which is about uniqueness and existence of solutions of differential equations. Well, we constructed a proof of the Picard-Lindelöf theorem for individual differential equations, but if you go through the proof, then you will see that it doesn't really use the fact that the unknown is a scalar. The whole proof, without much of a change, is going to work even if we change the scalar unknown to a vector unknown. So which means that we can change the an individual differential equation to a system of differential equations. Right? So, and Picard-Lindelöf theorem in this form still applies. So whenever we have a system of differential equations such that, so it is a first order system, so then suppose that we have our okay, so suppose that this is bold x, right? So vector x. So we know we have fixed the initial value. Yeah, so sorry, my handwriting is very bad. Let me on the handwriting, let me denote the fact that it is a vector by an arrow, right? So suppose that the vector x evaluated at t0 is given, is some, I don't know, some a. Then that is an initial condition. So by specifying the initial value of the unknown vector, we have introduced the initial value problem. So, and then the Picard-Lindelöf theorem tells us that a system of differential equations, whenever the right-hand side is differentiable in t and satisfies the Lipschitz condition with respect to x, it is going to have a unique, so the initial value problem is going to have a unique solution in a neighborhood of the initial point. So a little bit of terminology. So an autonomous system of differential equations is any system where the right-hand side does not include t explicitly. Right. So a linear system, well, means this. Let me just mention that. So here x, the bold x on print, I will denote it as a vector. So x is a vector here. So x is a vector, and at the same time, a vector can be thought of as a matrix of size n times n. N times 1. Right? So then P of t is going to be a matrix n times n. So x is n times 1. X prime is also going to be n times 1. And G of t is actually also a vector of the size n times 1. So then everything is consistent. So a homogeneous linear system is, well, a linear system with the missing plus gt. So if gt is 0, then we get a homogeneous system. Well, and then a linear system with constant coefficients is going to be, so the word coefficients here only refers to the matrix of coefficients, right? So which means that if we are saying constant coefficients, then what we mean is the constant is the matrix in front of x, but the free part plus g of t doesn't have to be constant. So that is not necessary. So let us look at a couple of examples. So the planet motion, that is a nonlinear autonomous system of 4-dimensional, right? So 4 unknowns and 4 equations. The system that we got from modeling the sweet water in the tanks is autonomous because the right-hand side does not include t. It is linear, but it is not homogeneous because we have the plus something in the end. And so the non-homogeneity is this. This is how we know that it is non-homogeneous. All right, so this part has to do with linearity, and the fact that it is autonomous is because there is no t here, right? So where is t? So here is an example of a linear homogeneous but non-autonomous system. Right? So if coefficients of the matrix are functions of t, but there is no plus free part, then it is going to be homogeneous, but